And let's welcome the next speaker, Černok from the University of Berlin, who's going to talk about the significance of ancient impacts recorded in Apollo 17 norites for the origin of the lunar MG suites. So Anna, go for it.
Hi, thank you very much. And thanks, Katie, for introducing that fantastic topic. Sorry, I'm starting my own alarm. Yes, so my talk is basically very well based on what Katie has introduced previously. I'm so happy to have seen her data now. My talk has two key aspects. One is ancient impacts, and the other one is lunar magnesium suite of rocks. And I will try to put some links between these two in my talk over the next 10 to 12 minutes. I cannot move my slides. Okay, now. Yes, so we have heard a lot yesterday and in the previous talk of why the ancient basins are important and why do we need them to establish this ancient part of the lunar history. Now we don't seem to have a lot of robust evidence in terms of samples of this ancient history, and this is one of the reasons why it has been proposed in many white papers from various agencies that these samples should be returned in the future missions. And as Katie has reminded us, we also need these samples to better establish the crater distribution functions and better understand the ages of the moon so that we can extrapolate them and understand the ages of other planetary surfaces for which we don't have samples. So far in our collection, we believe that the best dated crater is Imbrium. And the number you're seeing, the very precise number, is a compilation, a recent compilation of ages across various or all Apollo sampling sites, various geochronometers and samples. And not everyone in the community agrees that this age reflects the age of Imbrium, but it is a prevailing interpretation so far. And that is one of the aspects. The Imbrium samples have masked a lot of our samples that we collected. So we are starting to see a bias toward this age. Also, bias arises from using different chronometers. If we dominantly use chronometers like argon-argon, we are using a fantastic chronometer, but running the risk of seeing the most recent ages and escaping those that are much older. And those older ages can be revealed by robust chronometers like uranium-lead, especially studied in situ in minerals like zircons. And you have seen that this age of 4.33 billion years is now popping up in meteorites as well at many different Apollo sites. So far, we have mostly seen this age peaking in breccia, complex samples that are comprising several lithologies. And we have seen one study that I will highlight where this age is associated with one coherent rock type. Well, not only samples are suggesting this impact age at 4.3 that has been so far associated on several occasions with the SPA basin. Also, crater counting models are suggesting that many of the craters should have been older than 4 billion years, so ancient. And also modeled ejecta deposits suggest that we should find ejecta or melt remnants from the ancient basins in our collections, or at sites at least. The other aspect of my talk is the magnesium suite of lunar rocks. And this suite of rocks is kind of controversial. It has been traditionally interpreted to present the mafic intrusions in the crust. And in the lunar magma ocean model, it was formed early on. So crystallization ages are spanning from 4.1 to 4.4 billion years. After the layering of the mantle and the solidification of the first anorthositic crust, that allowed ilmenite accumulates and ore creep to drive mantle overturn. That then gave rise to formation and intrusion of these plutons. Now the interpretation is that these plutons were then exposed to the surface by various impacts, because the mantle, basically the mantle mixing has allowed crystallization of a lot of these creep-rich minerals in this lithology. Recent studies have provided useful insights into this final stage of what could have happened to the MG suite of rocks, namely using to their advantage these accessory minerals that are also datable. In the study by White et al., the 4.33 billion year age discovered by the chronometers was also associated with the textures in minerals that are implying very high temperatures above 2000 degrees, above 2300 degrees, that can only be achieved in impact melt sheets. So the question was, the interpretation was provided that at least one of these MG suite samples was directly crystallizing from an impact melt sheet. So that impacts that actually liberate these samples to the surface, not only just transport them to the surface, but effectively melt them and then cause recrystallization, so that the MG suite samples are direct crystallization product of the melt sheets. And we hope to continue this work with this perspective to investigate further MG suite samples that have to search for the evidence of the 4.33 event by focusing on geochronometers such as bedelliite, which is a monoclinic zirconia, that can at the same time retain the textural record of events such impacts. And in doing so, we focused on a very well-studied Apollo 17 shocked norite. It is often referred to as the most shocked sample from the Apollo collection. It is a coarse-grained rock, so it's a coherent rock type, not a breccia. It does not contain other lithostratigraphic lithic units within it. It's a coherent rock consisting of, you see two dominant colors in this ChemScan mineral map. One is brown, which is pyroxene, and the other one is an orthozitic blue. Furthermore, this rock was deformed at 4.2 billion years, and this is where the impact melt presented here in gray brownish colors comes from. This is when it was formed. And this was argued in our previous paper that when we dated phosphates at 4.2 billion years, and it is also supported by argon-argon ages 4.2. Nevertheless, more robust chronometers of this rock suggested what was previously described as crystallization ages at 4.3. And the question is, what kind of crystallization? Now, several studies studied bedelliite in these rocks, in this and in the sister samples of rocks, and they all found the range of events from 4.2 to 4.3, and this was usually interpreted as being, magmatic age of 4.33, so when the rock was formed, and then progressively deformed by an impact that occurred at 4.2. Now we looked at these bedelliites again and focused on the microstructure. And this is what we find. I appreciated Kate to show the results because these are indistinguishable. So we are looking at a bedelliite here that is showing 4.33 billion years old ages determined by in-situ SIMS analysis. So a spot, the beam size of the analysis is actually fitting this little mineral that is only a few microns, about 10 microns large. And we find these 4.33 ages in both impact melt veins of the norite, as well as in the coherent shocked but not melted norite lithology. On the right, you see the plot of the lead ages obtained by SIMS. Now, we further focused on analyzing the structure of this robust chronometer. So on the left, you have a backscattered electron image observed by the SEM, and you see a nice white grain that is bedelliite. When you look in the middle image in its internal structure, you see that it is a very complex structure. And when you analyze it, you see that the structure of monoclinic bedelliite, so the mineral that we are looking at today, contains various twins or monoclinic variants. Now, these variants allow us to quantify the phase heritage of this mineral And that means by studying the misorientations of these monoclinic variants, this is performed by crystallographic software, you can basically understand the structure, the previous structure, the parent structure of this phase. And in doing so, we discovered that these monoclinic arrangements that we see today were derived from a very high symmetry phase, a cubic zirconia. And that cubic zirconia, based on the various phase diagrams, is only stable at very, very high temperatures, above 2000 degrees. Now, these temperatures are, these temperatures are not achieved by usual geological processes, and because the similar structures were already discovered in another MG-Suite rock, troctolite, by White et al., they were interpreted to be formed in a superheated impact melt sheet. So we extend this interpretation to the observations we have here. There is the other second generation of badellites around 4.2. They are mostly found in the impact melt veins, very often associated with silica, and for petrologists that implies a breakdown from zircon, another zirconia phase that in its structure has SiO2. When it breaks down at high temperatures, it leaves badellite and silicon oxide separated. It's another evidence that this secondary event at 4.2 was also high temperature. Now, to recap the history of this rock, we see two events. One at 4.33, very high temperate event that led to formation of cubic zirconia. We don't say that this cubic zirconia was crystallized in that melt, but it was probably formed after a precursor material or a target rock that was melted in this huge impact melt rock. And that the ages that we record were basically recording cooling and reversion from that cubic zirconia to the current monoclinic phase. And that actually helps us understand that this entire noritic lithology, the original makeup of this rock that has plagioclase and orthopyroxene crystallized by cooling from this melt. As you have seen, this age is very often related to the SPA event. Another event at 4.2 we have recently discussed in a paper is possibly related to the Serenitatis formation. It is so far noticed in the phosphates and in the argon data, and also seen in some of these badellites that have been then reset at the first crystal is at 4.33 from the impact melt, but then they were shocked at 4.2 and reset their uranium lead clock. And this is the time where the pervasive deformation of this rock occurs, forming the impact melt, changing plagioclase to masculinite, so that the masculinite is the dominant mineral in this rock. And I'm recapping. So these 4.3 event, as you have seen, has now been observed in many lithologies, including meteorites, as we have heard, found at many different sites, but so far mostly documented in breccias. And these two MG-Suite set of samples are the only coherent rock types that could imply direct crystallization from the impact melt formed at 4.3. The set of events at 4.2 also recorded in these norites has been seen widely over the Apollo sites. And these rocks, the norites, the troctolite, are very special because they don't see the dominant imbrium deformation, which is probably one of the reasons why we so neatly see the older ancient events. The plot on the right side, these are various zirconia or zirconia-rich phases. The left cluster is from these rocks. You see that they are only seeing the ancient impact events, whereas the right-hand side is what we see from the rest of the Apollo 17 samples that are very imbrium affected. So these rocks are really special. And in terms of the big picture, I would just like to say that talking of these ancient impacts, we often extend the question to whether there was a lunar cataclysm at 3.9 or not, while seeing textural and geochronological evidence of so many craters that are ancient or older than 4 billion years. We're definitely suggesting that the decay of large impacts at the beginning of the lunar history was following an exponential decay. And I think I can wrap up with that. These rocks are very useful in looking at the ancient events, and Badeliate has been proven as a very resilient chronometer that can also record textures. Thank you.
Thank you, Anna. Great talk.